Recording in progress.
Where are my zoomies? Who's on Zoom? Caleb, can you hear me?
Yeah, I can hear you. My bad. I was trying to find the mute button or
Excellent.
unmute
Thank you,
button.
sir. All right, so we're going to go over something called Big O notation and efficiency. So you can literally make like a blank file for now. We're going to be pulling stuff from online and looking it up. I need to add new item, just a general source file. And this is the start of module 5. It's too bright. Why you make me turn off my orange?
What do you mean by that?
I have a screen dimmer so that like when you're staring at the computer all the time, it's not fucking killing your eyes. And every time I come in here, Josue goes, it's too fucking orange.
I can't see anything.
Does you know my laptop's a Trump laptop?
So what?
No, it's a stupid joke.
It's because it's yeah, it's orange, so because he's making a joke that Trump is orange, even though that's not what human color should be.
All right, let's wrap it. Let's bring it in so we can get this stuff through. We're looking at the Big O algorithm. So I'm going to open up this right here.
So where's this?
This is in module 5 and it's called Big O algorithm efficiency. No. If you want to watch these videos, you can later. I tried watching these videos with the class last semester and they're going to say the same shit, but in different ways. So like, why watch it with you when I can just say it with myself? So we got this. And so let me go over to my visual processor or my document camera here so we can talk a little bit more about what's going on here. So Big O algorithm. Big O stands for order of complexity. And what we use this for is we use it to measure efficiency of an algorithm. Okay. There's a couple ways we can look at this. How much space is the program taking up? How much memory is it taking up when we ask for input and shit like that? Or the other thing that's important is time. Time and space. Even when it's in the digital world, time and space are our main dimensions that we're worried about. And oftentimes, time is the limiting factor. We don't want something that takes forever. So what we're going to focus on is on efficiency based on time. We'll focus on being more time efficient. And it turns out when you're doing stuff at the computer, doing arithmetic operations is relatively quick. Any arithmetic operation is really quick. In fact, everything is really quick in a computer, but some things are quicker than others. Any arithmetic operation is fast. Something that goes a little slower but is still fast are comparisons. So the way we measure the efficiency of an algorithm in computer science, efficiency of an algorithm is based on how many comparisons need to be made based on like your input, like your input's going to be some array or a vector or something like that, some data, a set of data, not like a CN, but like if they see, well, you probably had to do a CN to get all the data in there, but at some point you're going, okay, what are we doing with this data? How quickly can we access it? And there's a bunch of different levels of complexity. The fastest is called O1. This measures how many steps to look up something. Very few things are O1. If we look at this table here, I'm starting to go off the screen here.
So one more thing is, so if we do O1, it looks up.
In fact, they'll call it O1 lookup. It means if you want something, you find it without having to search.
Is that an actual function inside?
It's not a computer function. This is just a way to measure efficiency of a program.
So like you make your own function. And you call it.
Yeah, if we have like a function that we're calling in the program, or even if it's in your main and you didn't do an external function, how quickly does the algorithm, the process take? And we're going to do it by counting comparisons. If we look at this table over here, they actually show the speed of it. They don't even show O1 because O1 is flatline. But the next fastest one is log base 2n lookup speed. What? Then n is faster, or a little bit slower than log 2, and log n is a little bit slower. And n squared, which is almost one of the worst ones we can get, is actually what ends up being a lot of things. So when we're doing comparisons, what kind of things that we know how to do in programming actually compare things? Conditionals. Conditionals do comparisons. Conditionals do comparisons. So this is your if, your while, do while, switch. But there's other things that actually have comparisons in it as well. Your for loop. So let's take a look at how ones go. What we're going to base this on is we're going to look at sorting algorithms. Let's look at sorting algorithms. Now, pretty soon we're going to start binary search trees. We're going to develop our own sorting algorithm based on a tree. There we go. But for now, let's use what's available to us. So if we come back over to, where is it? This module here, let's go back to modules real quick. And if we're in module 5, module 5 reading. Click on module 5 reading. Sorting algorithm animations is what I'm going to click on. So if you're looking at home, you want to watch separately, we're looking at this right now. So there is a bunch of sorting algorithms. There's insertion, selection, the bubble method, the bubble sort, the shell sort, merge sort. And they base it on how like the the worst case scenario is how efficient a program is. So like if everything is the worst possible thing could happen, how slow is it? So like if it's already almost nearly sorted already, things should go pretty quick. If it's in the exact opposite order, some of it you would think it's going to take a while, depending on how it sorts, but some of them go really fast. If it's in random order, as most things come in, though, you just put shit in, and however it comes, you enter it. Random is what happens most, but we can actually play them all at once, and it's less helpful to do, but it's worth seeing. I click Play Me. We're looking to see which ones finish sorting the fastest. And which ones are worth more, so what's the slowest? So they're going through and they're sorting them, and some of them are already done. And look at that, bubble sort is still fucking going, selection's still going.
So like, quick 3 and quick 1 is the fastest.
Yeah. And in fact, that's why they've got quick in the name. But they're a pain in the ass. Some of these are harder to understand coding wise. What? Sometimes it helps to look at a single column. Like bubble was really slow. Which one of these? Sometimes it works better for some things than others. So if I look on bubble, bubble got nearly sorted really fucking fast. But everything else reversed it was its worst case scenario kind of thing. If we look at quick, it didn't look like it was going that quick, actually. Are we sure that was faster than bubble?
What was the last one?
Yeah, but quick wasn't that much fucking faster. Quick 3 was pretty fast.
No, it was quick 3 and then shell. Oh, no.
And you guys kind of see the way the red arrows are going, kind of, we can get an idea how the algorithm's looking.
So it doesn't do like a middle function, like how we use like goes to the middle and search it.
Each one does its own, each one is a completely different format. Watch what happens with quick. Now all the stuff in the red happened in the beginning of the red, and now it's happening in the middle. It's breaking it down into like sections, doing everything within a section. When we do bubble, it's like kind of going through the whole fucking list one at a time and putting the lowest one at the top, as you can see.
So we would really want to make a quick 3 of shell on a program. Because it would be more quicker, but I would expect it to use more RAM than the bubble.
Look at the code on quick. This is not in C++, but look at how complex this is to read. There's recursion, there's pivots, there's a bunch of shit going on. And now look at something like, let's go back and look at like the bubble. Look at how easy the bubble sort code is for, it's a lot shorter. There's a swap function. If if AJ is less than AJ minus 1, switch them. So some of these are easier to implement than others. Over here, they suggest what they are. Let's look at doing some of these. I don't know what code this is in. Click C++. Will give me the code in that? Nope. Oh, that's an interview guide. How to interview for prepping for a tech interview based on where you're wanting to get a job at.
I know that you can search up a bubble function.
We're gonna look up bubble sort, C++. We'll grab the code, we'll drop it into Geeks for Geeks is usually good. Don't do this on a test.
That's cheating on a test.
Yeah, it speeds shit up a lot. Ooh, they're doing a vector there.
I know that Mr. Redden did this very well as passes.
I wanna, for comp sci 1, he did bubble sort.
Yes, he did bubble sort. Like that was one of.
I need to slap him. He needs to get slapped.
That was a great homework.
You gave us the.
But he knows it's like not in the class. Like the sorting he knows is in CSCI 2. He knows this. He just said, use this and run with it without talking about it. He
You talk about it.
did he say who came up with it and the fucking history of it? He fucking knows a little bit too much about the people that wrote some of this shit. He's a
So,
little obsessed.
so how, he talked about this for us in like the first week of CSCI, when I took it.
Ooh, I got caps lock on.
It was like so weird, because I'm like, okay,
In Seaside 2,
in this class, the first week.
I'm just gonna copy paste that real quick.
That's why I know about the story, because he mentioned it, like, in the first week.
Let's go in and put in the stuff we need, IO stream. We want random, so I'll include C time. Maybe we'll want to have strings in here. I'll add string. Standard library. I don't know what I need for now. I think this actually does the same thing, but fuck it. I'm already in the habit of doing it. All right. What else is missing here? Oh, this is taking in a vector. So we're going to adapt this so it's not doing a vector. They've got a V here. What? I said we were copying and pasting it. Let's make an array.
Also, it's this one, so
Let's call it V. Do not make me fuck you up. Ooh. Let's say with constant n equals, let's make it small to start off with. What am I missing here? I'm fucking brain farting. Oh my god, I'm totally brain farting. How the fuck do I set up an array? This is bad. I'm so fucking brain farting right here. Fuck.
that's probably the worst thing.
Yeah. There we go. And they've got B down here, so we'll use that. So let's just do a quick for loop. Print I equals 0. That's not a 0, that's an O. I less than N. I plus plus. VI will equal 1 plus rand. What do we want to do? Rand mod what? Say 1,000. That's wrong too. Bracket it. What the hell's the parenthesis? Oh, wait. Wait, okay, say that again. I had it outside. That sounds right. Oh my God. I am just having a fucking, Jesus Christ. This is bad. You would think I'm drinking or something. This is just tea. There's nothing in it. Oh my God. But
Imagine there's vodka in there without you knowing.
do they have a print function in here to make this real quick? No. All right, let's put a print function in here. Oh, fuck it. We'll just do a print in the goddamn code down here. C out VI. And then we will have it do its algorithm, and then we'll make sure that it's actually sorting. Let's make sure this thing is working. This says swap, but we don't have a swap function. Where's the swap function?
Oh, it's all the way down.
I guess you could use that one with,
Oh, maybe it's just using the one swap from. Gonna run? Oh, we need some C out in there. That looked like shit. I don't know where the list was. Hold on. And then after the loop, we'll do a C out. Need some space in there to make this look more presentable. Okay. So we're going from, it was out of order, and now we've got, interestingly enough, 42 was the lowest number, and it started in the right position. So the swap mechanism is working. I'm going to comment out this because we don't really care about what this is doing. We're going to go through and set up a counter for it. So what I'm going to do is I'm going to make an integer counter. And we'll initialize it to 0. And then, actually, I don't even need that one. So what we're going to do is every time we do a comparison, we're going to increment the counter by 1. Okay. So a for loop, every time it goes, we're not going to count the one where we're setting up the array. For checking efficiency, don't include the data array setup. In your count. I'm just going to delete that for now. We don't need that info now. So every time I see a comparison symbol, I'm going to do a count. So every time a for loop goes through, once it goes like when I equals 0, it checks to see if I is less than, in this case, 24. So every time the for loop triggers, it goes off. So we're going to increment the counter by 1 here. That's one way to do it. You could do count plus equals 1. You could do count counter equals counter plus 1. However you want to do it. They all get the same thing. And so every time it does that, we're going to do it. We've got another for loop here. So we need to do it, have again go off in here. The if loop has a comparison as well. So I need to count it, right? Where should I put the counter for the if statement? If I put it inside the if statement, will it count every single time it does a comparison? This is just like, how does an if statement work? If I put it in here, I need a bracket. If I put counter in here, will it count every time that comparison is made? No. It will only count when VJ is higher than VJ plus 1. So for an if loop or something like that, either put it beforehand or after that hand, but it needs to be near there. So I'll put it here. I'll say this one is for the if statement. It must be outside the if statement. And for loop counters can go inside. So we'll let it go through and do what it's doing. Maybe after it's done, we'll do a C out of, we're doing bubble sort here. So bubble sort on N entries took counter comparisons. Let's just see, 25 is a bad number to use. Let's do a number that we can get a better feel. Like a multiple of 10 is usually better. 10's too small though. Let's go like 100. So it took 100, roughly 10,000, right? So N equals 100. Comparisons was approximately 10,000. What's the relationship between these two? 100 squared is 10,000. 2 zeros and then 2 zeros, 2 zeros, 100 times 100. So bubble sort is ON squared. This is one of the slowest ones, and we saw that when we were running it. And each time we run this, it's going to be a different value. I did not institute RAND. I didn't even. This RAND times 0.
So that some people in like Ultra use that one.
That
But every time we open it, I mean it's random, every time we open it, it's the same.
they may not have included C time or something. I don't know. Did we really hit 9999 again by sheer chance? All right, I'm turning on the fucking. Let's turn that back on. $631.35, and if I run it again, am I getting $631.35? No, I'm not. I'm getting different numbers each time, and yet it's still taking that. So this thing doesn't speed up at all. This is stuck. It's fucking literally stuck at N squared. Other ones will fluctuate because, oh, I know this one doesn't have a break in it. Other ones will be like, if it's already sorted, we're just going to break out of the loop. So let's go look at another one and compare something else. What's a good one to do over here? Let's come back to, that's not what I wanted. Right here. I don't want to do quick. Let's do another one that's of average speed. Merge wasn't bad. What's merge look like? C++ merge algorithm. Ah, nice little picture. So it's got like an array and it breaks the array in half and sorts these, puts them back together, and then sorts those. Probably goes when it gets to here, picks the lowest one from each one and just drops it in. So, wow. This whole thing, look at this thing. God damn. Can we do one that's fucking less rough? All right, fuck doing. There's a lot there. How many, like, literally is what's going on here? Okay. Let's see. This is the what the hell is this one down here? Why is there two? Void merge, and then we've got does merge sort call on merge? It does. Ugh. All right, fuck doing that one. What's heap look like? How bad does heap look? Eh. Selection looks simple. There's no, it looks a lot like the quick one now. How does insertion work? Ah, it does two comparisons in each loop. That's interesting. Let's do one that has a changing speed. Invariant might mean changing speed, because I know shell has a break in it. Insertion sort. Something we can set up easily in the time remaining rather than. Oh, look at them. We'll just grab that real quick. Let's steal their fucking print array. Bam. Print array stolen. And now our insertion sort. I just need that part. So I'm going to come over here and in the main, I will do it. Well, shit, we can do it after this. So I'm going to make an array. They have R down there, so I'll use that. R bracket N. And we'll just populate it at the same time. And I don't want to do another random. I want it to be the exact same numbers So I'm gonna say array I equals VI. And then we'll set up another counter for, which one are we doing? Insertion? Insertion. Count insert equals 0. All right, so that generates our two arrays. This array is bubble sort array. Since people are going to want me to copy and paste this into and I'll throw this down here and change it to say insertion sort down here. Huh. Okay, so the insertion sort is here. And what do we call it? Count insert? Count insert. So we will increment count insert every time we see a comparison. We see one in the for loop, so we'll put one there. These other operations go quick, so we don't count them. So this is going to automatically do 2 checks right away, right? So I'm going to do count insert plus equals 2 here to represent it going off once. And each additional time it goes off, it keeps doing a loop. It should increment again. Maybe this might be better as a do while to check our stuff. So I'm going to put this in the do.
What's actually the difference between the do while and the while?
The do one happens is guaranteed to happen at least once. Wait, I don't want that. Because it may not happen once. That's the point of using. All right, so how can I make sure? So if it only goes off once, it's got to count it. And it's got to count it. It's got to count it at least twice. Because, well, no. We're going to put one inside the loop as well. So let's see, if it only goes off once, it's got to do, like if the while loop triggers once and it does the comparison again, we should get a total of 4 because it's doing twice each time. This would have that happen. If the while loop goes through twice and then stops, it's doing 6 comparisons. We would get 2 each time from this, and that would be 4, and then the other 2 out here. So this accounts for the final. Maybe I'll put this afterwards so it looks. This accounts for the final comparison that isn't triggering. And these are for each triggered condition. Okay. And when that's done, let's speed this up, copy this line, come down here and make it say insert. CEO insertion sort. All right, this should give us. Do we actually need to print the loop? This is too long. I don't like this. Oh well. The bubble sort's there. I'm going to turn this off. We don't need to see the thing right now. We know it's working. Does it make sense what I've been doing so far? That's the important part. We got to count every comparison opposite operator when it happens. And we're only doing it on the stuff we're actually checking the algorithm for, not like the data setup. Is it 9999 every time too? Wow. We know it's making a different array each time.
I think you forgot to make the counter count insert instead.
I did. Good call. Just reporting the bubble sorts one. There you go. Look at that. Despite doing a double count on a bunch of the loops, it looks like it takes half the time. We will. We're gonna run it a few times. So it's getting a different amount each time. But they're all around 5,000 rather than 10,000.
How is even that one's smaller than that one's
Like,
great.
400, 4,000, 2,000.
So there's some variation in there. Let's see what Wikipedia says about the insertion sort algorithm. Well, that's fun. It does a little animation. Worst case is ON squared. Best case is ON, which is weird because it's not looking anything like ON squared. So, well, it's something like half ON squared. If we look up bubble sort, maybe I'll make another page so we can. Yeah, that's a helpful visualization. Thanks a lot, buddy. ON squared. It's got the same setup, average performance, ON squared on this one. Insertion, average performance is ON squared. Let's take a look at like the merge one. We got time. Merge sort is on order of n log n. I wish they didn't use log n like this because they really mean log base 2n. And when you don't have the subscript, it very much implies 10. So it's very fucking misleading. But let's go. Let's grab it from Geeks for Geeks. Let's see what we got. C++, merge sort. That looks like the same motherfucking picture for the insertion sort. No, it wasn't insertion, was it? Was it the selection one or some shit like that? I don't know. Oh, not merge. I did look at merge. Shell. Let's do shell. Shell's, that's the one I want to do. I wonder if it'll be just as easy to just go shell sort. Oh, it's a variation of insertion sort. And yet it's faster. Ew. Ew. It was n log n rather than n squared. Let's see. I am going to, this loop ends here, that loop ends there. This is the algorithm.
How hard is to pull that?
That hard. Coming up with the algorithm is the fucking hard part. Like this is breaking it, like they're like, oh, let's break it into half, sort those, we'll break those up until they get down to 1 and 1. They only showed 4 here in the picture. On the insertion sort, they only show, what? Okay, well, I'm not doing Discord right now. Is it Juan? Tell Juan to show up to class. He's like, this motherfucker. All right. I know, he told me why he's not here. I'm just fucking with him.
Is he in Zoom? Is he on Zoom? During this?
He is not on Zoom.
Oh, you should use the at thing.
Yeah, he'll see it eventually. I don't even need to see it right now. All right. Let's do one here. They used array again. I'm going to change these to all say R2. Because we got array going on for the one up top. And we got to make another one called array2 then. And we need a counter for this one too. Int count shell. So this is always a dead giveaway when dead fucking giveaway when students are cheating. You got like some shit like I++ here, I++ here, and then I come down and I see some shit. Where was it? I+ equals 1. You fucking change your how you write your for loops. People don't do that. People are consistent with how they write code. But doesn't matter for this. We're going to use it. So this is our for loop. And this is our shell loop. So let's see. It is going off. Fun that they use gap. Start with a big gap, then reduce the gap. All right. I see a comparison here. We're going to count. I see another comparison here. We're going to count. I see two comparisons in there. So we gotta count twice every time the for loop goes off. You would think this should be fucking slower. There's a lot of, but it's basing it on some shit like that. Let's copy this. Let's make it say shell sort. Make sure I change that to say shell. Look at that. Fucking way less.
For some capacity.
We could look up how quick quick 3 is. But it's consistently just a little over 1,000. Now we start with 100, so it's over 10 times as much, but still, it's nowhere near 10,000.
What's the comparison point?
What? When you say is something less than or is something greater than, that's a comparison. This right there.
But why I don't understand the concept how fast it growing.
The more it takes to do a particular n, the slower it is. Because it has to do it more times before it gets to the end of the sort. Does that make sense?
Trying to do so.
Okay. Count to 10,000 or count to 1,000. What do you think is going to take longer? Please don't actually count to 10,000. Counting to 10,000. It's going to take longer. It's got to do it every single time. It's the same idea. If I have to do the comparison, it's like counting a number going 1, 2, 3. Same idea. Every time it does a comparison, we're counting that as something that affects speed. So the more you have to do something that, even though it's really quickly, picture dealing cards. Some dealers can do it at fucking blinding speed. Some people deal fucking slow.
You're getting a bunch of random numbers.
We're doing the random numbers just to make sure that we have, like, we're not setting up the system.
Because if you have 1,000 numbers, from 1 to 10,000, what you can do is like, I'm trying to think about it. Instead of counting in 1, you're counting in 10, for example.
We're not. We're counting every time we compare. We have n number of data values. Here we did n equals 100. Let's drop it down to 10. We've just got 10 numbers. Now, for 10 numbers, the bubble sort had to make 99 comparisons. So it had to do an operation that takes a little bit of time, 99 times.
Wow, the shell only took 53 compared to the other two.
While the shell only took 53. Which means it took less time to do it. Picture these as like minutes on taking a test. They're both, like, let's say we've got 2 students and they both get 100%. So they're getting the same answers, but one student took 99 minutes and one student took 53 minutes. Whoever's doing the 53 minutes might have had more efficient studying, but in this case, we're just calling it efficiency. They're faster. Speed on a computer program, like 100 entries isn't a lot. Let's bump this shit up to fucking 10,000. Let's do 10,000 numbers.
How efficient is sorting to even more?
That didn't have much of a time gap. Let's up it to 100,000.
that's what it's doing.
Yeah, it's
basically-
sorting, so it's
it's
telling you,
taking all that.
it's telling you.
Oh, I broke it.
It's doing until it's all in all.
So, the smaller-
Yeah, so just some random numbers and we're gonna put it in,
Okay. So it's taking all of them and saying like this one is smaller than this one and this one's smaller than this one and.
yes, and they need to be in numerical order when they're done.
Oh, okay.
They may not be 1, 2, 3, there's gonna be gaps in there. And if there's repeats, the repeats, in fact, with n equals 50,000, there's going to be repeats. Unless I make this like rand mod 100,000.
Oh.
Well, like 50,000, hopefully it doesn't break it. Notice it's taking some time.
Great, since you have a bunch of that. So,
Actually, this might be better. Let me put the insertion sort comment below insertion sort. That's the shell sort. This was insertion sort. So we can kind of like get a feel for how long it takes. So this one is doing the first one we did with the bubble sort. And it's sorting 50,000 numbers. Oh, wow, we broke it. We got some fucking negative numbers going on. We went larger than the largest possible value.
Oh, that,
We broke the fucking system.
I mean, when you go beyond that, that's when I go to the other side, right?
Yeah, it jumps over to the negative side because it needs more numbers. So maybe let's not go 50,000. Let's go 20,000.
Number like, if you can like input.
It depends on the system.
Jesus Christ. Compared to the other ones, the shell is way quicker.
Yeah.
It's already told me that like in accounts when like billionaires have like a bunch of numbers in their account. I mean, big libraries or something to make these really big numbers.
Yeah.
Wow, like compared to the bubble to the intersection.
This-
sort, it's not that much difference. There is a big difference, but it's not as
Well, this is
much-
like half.
Yeah, but it's not like as much of a difference from
Right.
intersection to shell. Like,
In fact, remember when we did n equals 10? We had 53 for shell and 100. Like shell was only half as fast. But now we've got 1 million versus 400 million. So like depending on the data size, it really shows like the bigger the data set, the more shells shows its efficiency. When we did n equals 10, it sped it up twice. It took half the time. Here, it's taking way less time. So, but this is the point of this is how big O notation works. And they list efficiency on algorithms based on the end that like how many things you're trying to sort or how many things you're trying to work with. You're not always trying to sort, but that's a common one to do, so it's easy to check this. And you want to like this was from if you look at this reference here in our modules on Big O algorithm efficiency, we had this PDF. That ain't it. It's right there. You kind of like the more it's the lower it is right here, the better. So log 2n is faster than log n or n. And n is faster than n times log 2n. And the more it is, it starts taking exponentially longer. I don't even know what goes at 2 to the n. That's fucking really slow. Like every single time you enter data entry, it doubles how long the processing time. That's really what 2 to the n means. If we had 3, it's going to take 8 steps. We have 4, it takes 16. If we have 5, it takes 32. Every time we add another data value, it's fucking doubling. That's super fucking slow. That's like Josue doing his fucking test slow. he did some props on like whoever he's reviewed. He likes to pester the shit out of me. So he like messages me yesterday. I want to make sure I'm doing a good enough review that I get the full 10 points. Is this good enough? And he sends me like this fucking essay for one person. I'm like, yeah, that's a good one. That's well done. You're gonna make it the rest of the students fucking look bad. Likely, there's no reason for it to do more than that. That's the slowest it will take.
Something like wrong is that I think too much about something that is really simple, and I think it's like, I don't know.
Well, you know, your review, you were giving good feedback. You should read your peer review feedback. It shouldn't tell you who gave you the peer review feedback, but
But now you tell them.
No.
They're gonna take it personal.
you just wrote a long one. I don't know if you did the other ones that way.
I did mine, you know.
Triumph was a fucking crackhead on his test.
They wanna take tests.
If you reviewed Triumphs, you will know it because his like name array had like fucking 100 names or some shit. How many names were in it? He had a lot of names in there. And I'm like, "Gee, where the fuck did you get all these names?" Like I was pulling names from this and this and this and this. All right, that's kind of all we got for today. We did 3 sorts, showed the speed. I'm not testing you other than maybe like on the setup, like give you a small array and say, do the count on this. You don't need to tell me the order of complexity, but you need to show like how you would modify an array to count for this sort of thing. And it'll be like on the practice exam, you'll see it. So you don't like, this is more of a learning tool rather than anything else. All right, GTFO. That's what GTFO means. Let me say it in the long form out. Get the fuck out. Or if I wanted to say it like Redden does, get the fantastic out. You've heard him say what WTF means, right? He says WTF is, wow, that's fantastic. Just makes you want to just like, yeah, shut the fuck up, Redden, that ain't right.
Someone just said, if the day today was to be not the space machine, everyone would say,